this is a video of me doing interview with an AI. Let's see. I should be able to log in in a moment. So John Sharma is my interviewer. It's nice it has a name actually. Yes, I'm ready. Yes, I'm ready. So I have worked with strong to atoms on light scattering, but also on building the experiment itself. So I work building the atomic physics experiment, I work set up the laser system, the frequencies of the locking, and so on. And this was the experience that I would say that I have the most experience in my life. So it took in total like 6 years for me to work with it. So it really helped building all my technical knowledge, working with atoms, but also on the control system. I would say that the most difficult part was because we have to change the control program. So we have a previous version of this control program that was quite slow, and this decreased a lot the per production, the rate of the experiment, how many clouds can we generate in such an amount of time. So I would say that this was the most difficult part, to be able to like really reduce this to increase the data taking, because we have to integrate for very long periods to extract the data that we need because the signals are low. So in this way I would say that change this and making it still able to communicate with all the other parts of the experiment was the most difficult task. So for Python, it was mostly actually Python. I would say that is the most used language right now in our experiment. So we use Python for two things: for controlling the experiment, so the overall background that communicates the boards that are used to control the experiment, but also with the computer to generate the experimental sequences, because these experimental sequences they need to be very time precisely. So we need to have precisions down to microseconds. And then all these interfaces done in Python right now. And in the other task, we also use Python to analyze the data. So to collect the data, it's the biggest part of my PhD. We need to take data from different equipments. So I have three main equipments that are used to acquire the data. And these I'm talking about lots of data, things like 100,000 points. So I have 100,000 points, but I'm 3 because I have 3 equipments, right? So I need to integrate this data, check for the consistency. If it's right, then I need to sort all this data by atom numbers or by other parameters that are relevant for that experiment. And with this, I can actually make my plots to analyze the results that I want to obtain. So this was the most used Python part, and for MATLAB it was also mostly used to run simulations. So there are two types. We do these random walk simulations, which is the simulations where we basically calculate distribution of probabilities to calculate the path of the photons inside the cloud. So for this we have to, like, it's really a trial thing, so it's similar to a Monte Carlo method, I would say. And we have other simulations which are the coupled dipole model simulations, in which we generate the cloud position, the interactions among the atoms, and have to diagonalize a very big matrix to be able to obtain the interactions between them. And I would say that this is how I use MATLAB and Python in my experiments. So for synchronize this, so the overall background, it was a program that was done actually by other people, not us. What I did was implement this to our experimental solution and then implement our equipment inside this, I would say, background. So to communicate with different equipments, what we do is to use this protocol that's called ZMQ, which is zero Q message, and zero message queue actually. And this protocol, it's basically, so the idea is that I have a main program that generates the experimental sequence, and this is later passed to these controlling boards, and then all the equipments, they are basically triggered to be sure that they are going to generate the things that need to be generated. So I have a master clock that defines the time of my sequence, and this master clock controls through triggers and turning on and off all the equipments that need to be done. So this is how I'm sure that I have the time precision that I need to have using this master clock, and that controls these boards, and then the boards send the signals that are going to control each one of the equipments. I would say that it's not so since I'm not pure a programming person, like I'm a physicist, but I'm very interested about programming, I don't think that it's actually, my time is not worth to develop actually my own main solve, right? This software works very well. I think that what I could do is actually I could work integrating more the equipments that I have inside these backgrounds that was developed by these other people. So I would say that what I could do to engineer better my experiment is first, okay, so there are several technical things that need to be adjusted to be sure that the reproducibility of my experiment is good enough. Because right now, so we don't have good reproducibility, but it's mainly because of external factors like the temperature fluctuations and things like this. But these are more on the technical side, more, I would say, on the hands-on side. I would say for the programming part, there are a few parts of the equipments that are not actually precisely integrated. So I would say that I could integrate more this equipment. For example, we have a time-to-digital converter that we use to acquire the data from the photodetectors. And this program, so it has its own interface that I wrote, that is also wrote in Python. So I think that one thing that is to be good is actually to integrate this whole interface that it has inside this main background that was done by these other people. So about the data output, I would say that it's not super important, because right now in the way that we work, we already have data that have very different formats. So to integrate all this data, we use these hierarchical data files that can support images, arrays, vectors, text. So it's a type of data that can actually already support integrates different data files, which is something that is natural for our type of experiment. So I would say that independent of the equipment that I get, probably one of the data that it's going to give to me, it's already one type of the data that we are actually use the experiment. So this is not important. I would say that is what is most important. It will be if you have an equipment that already have like a good library, or at least that can be used to develop a good library in Python that then I can use to communicate through ZMQ and these other codes. These other protocols, I'm sorry. Can you repeat the question, please? I would say that the most important thing is to be sure that actually, as we do with all equipment, we characterize them as we need them. So we characterize the time that they need to be triggering, once they are triggering, how much times they need to start acquiring the data, and if this time it varies, right? If this time for some reason could have a jitter, which means that I have an average time for this experiment to be activated, to be getting the data, and also how much this time is varying. With these characterizations done, I would say that in the way that my experiment works right now, I can integrate any equipment. Because if I know the delay that I need to activate the equipment for it to start to acquire the data, then I can just program my trigger, because so these boards, they generate triggers to all the equipments, and I can easily check and select how much is this delay time, and I can also take into account the jitter. So if for example I have a problem for jitter, I could just be sure that when this equipment start actually taking the data, I have a signal, so in the way I know exactly where it started taking the data, and for the delay I can just program it before or after. So in the way it is very easy to integrate the equipments. So I would say that what I need to ensure is that I need this equipment to be triggered, and all these other parameters to be actually well characterized. In this way I can just seamlessly integrate it in my experimental sequence. So when I have to develop this, the thing that I would say that the most important thing that guide my approach for this was to be sure that I will be able to connect the data from different equipments. So in this way, what I did is I actually stabilized several, I would say, like flags to check to be sure that I'm connecting the data correctly. So for example, as I said before, I have to integrate the data from 3 different equipments, and all this data, they are time synchronous. So I have, let's say, the same data for the same experiment. I have this data split in 3 different equipments, and all this data were taken continuously. And so in this way, I need to be sure that I will be able to know when I start, when I finish, which one to be sure to merge all this data together. So what I did is I implement several flags. So for example, for one equipment, every time when this equipment starts to run, it takes the actual shot. So we have a shot number that runs continuously. And so for this equipment, every time when it starts to run, it takes the first shot when it starts, and I know that continuously it's gonna take, I don't know, 100, 200, a fixed number of points. Then at the same time, I have another equipment taking data, which are pictures of the atomic cloud, and this one were also all set up by a shot number. And in a third time, I have this equipment that actually controls several others, and this one was also responsible for acquiring information for different sources, like for the text or temperature measurements and others. And inside this one, for everyone, I also have the shot number. Another thing that I did is that I made the equipment to give back values for the main server, to be sure that when they are taking data, they are giving some values, which were like a 1. right, in binary numbers, and when they're not taking data, they're giving zeros. So in this way, I'm sure that if this equipment, if one, for example, if one of the equipments run 1,000 times, but the other just take 800 measurements, I'm sure that for this 100 times, only 800 will have a value that says, okay, this is actually a good value. So I have like these two main ways of be sure that which measurements I should integrate and when they start and when they finish. And in case I need, as a third way, I could also check for the time when the data was acquired. So for this, I also synchronize all the computers at the same time with the same time in the same time span, right? All the computers are synchronized to be sure that they are measuring things at the same time and register the time when these things were measured. If what I could not ensure that I have, how can I say, that I have a good synchronization. So to ensure the synchronization, I have this time, I have this I have this number, which I call shot number, which is unique and grows continuously. So I'm sure that for experiment that it was run, there is a shot number. So in this way, I'm sure that I can synchronize them. But if I have problems with the synchronization, what would happen is that one of these equipments won't generate the imaging, right? Because for the next shot, when it generates, it's already the next shot, and then it's going to have a different number. So if for some reason I realize that from these three main blocks that I need to integrate, if for some reason I realize that one of the images or one of the files were not present, I can just remove this shot. If I have the three of them, then I'm sure that everything was done correctly and that I can use this data point. Of course, other things could happen, like I could have problems with the lasers or other things that I actually not been monitoring. But I'm sure that these things, because my experiment is quite precisely, if I have problem with the frequency of the laser or anything like that, this would appear as a ausence of the cloud, as a higher temperature. So this would appear in other parameters that I'm monitoring, and in this way I can do a post-selection to remove the shots that were executed for some reason were a problem. So my research is quite finished actually, so I don't have my data taking is done. So I don't have to continue, I would say, improving the system, because once I finish my PhD, I won't be responsible for running the experiment anymore. But I would say that if I continue working in the laboratory, I would be sure about implementing, actually making the whole course of measurements done in just one language, which is Python. Right now we are currently using at the same time Python and MATLAB, because we didn't manage to integrate the cameras that we are using inside Python, because there are actually no support for it. So I would say that I could develop my main library to integrate my cameras also in Python, and in this way I will have, I would say, just one programming language controlling the whole experiment. So when I'm running a simulation, of course, that I would say that the easiest thing to do is just to be sure and to check the parameters that the results that the simulation gives in parameters actually where we have a theory that supports itself. So for example, I'm working in my experiment in a dense regime, which means there is a regime for which we don't have theory, but for the non-dense regime, the theory works very well to describe the behavior of the atoms. So what I do is I use the same simulation to generate the results for a regime where I know the behavior, I know the results that I should get, and once these results match the theory that I'm interested in, I can run this same simulation in another regime where actually I'm going to generate my experimental points. And in the same way, in the experiment, I also first collect data in a region where I know how it's the behavior, where I know how it should work. And in this way, when I collect the data in the high density, I can ensure that the effects that I'm seeing is because of the parameter that I changed. In this case, the density of my spatial systems. And for the simulation, this is how I'm ensure that it's actually matching the results. Of course, the experiment, in the way that I will work, the experiment is the most important one. So if the simulation is not giving the results generated by the experiment, I adjust the simulation. Because what I measure in the experiment is true, but it's possible that for my simulation, I haven't included all the facts that are necessary to generate my experimental points. So once my simulation is not matching my experiment, I adjust my simulation for it to match my experiment. The simulation that we do, they don't need to be actually so optimized. So I would say that it's actually so necessary to implement the most advanced technology. But some things that we do is that we use parallelization, because a lot of, so the simulation itself is not complex to be calculated, but it's just long. And at the same time, I need to, when I do the simulations, I have a lot of errors that could happen just because, for example, it's not that an error, but I want to obtain an average behavior. It's the same of my experiment, right? I also run my experiment several times to obtain the average behavior, and with the simulation I need to do the same. So what I do for the simulations, I usually we make use of parallelization to be sure, so we can calculate the same thing at several times. And I would say that's the most advanced things that we do.